Hi, the title of this presentation is Basic Use Cases of the Use Model Validator. My name is Martin Gogolla. I'm from the University of Bremen in Germany. The talk is about use. Use stands for UML-based specification environment. Use is a UML and OCL design tool. The model validator is a component within Use. It is a component for constructing a UML object diagram. Starting from a UML class diagram, the UML class diagram may be augmented by OCL invariants, and in addition, for working with the use model validator, you need a finite search space for describing the object diagrams that you want to consider, and the finite search space is determined by a so-called configuration. The use cases that I'm going to talk about are three use cases. The first use case is about object diagram construction. The second use case is about partial object diagram completion. The third use case is checking a property like invariant independence. And there is a number of other things that you can do with the model validator. There are a number of other use cases also available. Let us go to the first use case for object diagram construction. You see an overview over here. We see here a UML class diagram, and we see 1, 2, 3 object diagrams. And these object diagrams have been constructed automatically by the model validator, this component inside Use. Let us look into some details. The class diagram that you see is a quite general class diagram which describes general graphs. You see a class for nodes, and you see an association that describes the edges in the graphs, and the edges are directed edges which have a source and which have a target. And the class diagram may be augmented by constraints, in this case by an invariant. And I have added an invariant. The invariant is called isCycle. So what is required here is that the underlying graph is a cycle, or builds a cycle. And if we now look into the details of this invariant, what is required here? Well, what we require is that for every n, which is a node object, the following is true. Well, there is exactly one edge which is going into the node, n.source size is equal to 1, and there is exactly one edge that is leaving the node, n.target size is equal to 1. And what is required here for each node n, when you start from the n and you consider the targets of the n, of the node n, and then you build the transitive closure of this role name target. So you consider all nodes that are reachable into the target direction starting from this node N. Then you reach all nodes here. The configuration, this constraint, this invariant, was fed into the model validator. The model validator considers the constraint when constructing the underlying graph. What is also required in the configuration is that I have required that exactly 5 nodes should be present in the resulting graph, and when you consider this invariant, and when you consider the requirement to have exactly 5 nodes, then you will end up in a graph which looks like this. So the model validator has constructed a graph which is a cycle consisting of exactly 5 nodes. A configuration always takes care that the number of considered object diagrams is finite. You always have to present an upper bound for the number of objects in a particular class, which comes from the class diagram. A second constraint is specified over here, and the constraint specifies that the underlying structure of the graph should be a tree. I will not go into all details here. Basically, what is required here is that one root node should be present and all other nodes should be reachable from the root node. The root node has no ingoing edges, and starting from the root node you reach all other nodes, and for all other nodes all other nodes have exactly one incoming edge. And you see one choice here, one option for building a tree with, again, 5 nodes under this constraint is presented over here. The constraint can be even more involved. What is required here, I have called the constraint is double linked list. We again have here 5 nodes, and each 2 nodes are connected with 2 edges. One edge going into the upward direction, and one edge going into the downward direction. And you may understand this graph here as a double linked list. So what we have seen here, we were starting from a class diagram, and we have added various constraints. We have considered also a configuration. The configuration bounded the object diagrams that we consider to at most 5 nodes, to exactly 5 nodes were fixed by the configuration. And you see that depending on the invariant that you feed into the model validator, you obtain different graph structures over here. The second use case, I have called it object diagram completion. The class diagram looks a bit different. The class diagram is about a murder, and imagine you're an inspector, and you are called to a place, and you come over particular findings, and the findings tell you about persons, possible facts about persons who might have committed the murder. The findings tell you about how the murder was committed, and the findings tell you about where the murder took place. This is represented here in a ternary relationship between the classes person, tool, and location. Each class here has a identifying attribute, string valued attribute name, which identifies the person, the tool, or the location. And now consider the following situation. You come to a castle and you have you see that there are 7 findings are available, and the findings are written on pieces of paper, and you read now these findings. Well, let us consider the first 3 findings here. Finding number 1 says, if the murder happened with a hammer, then it wasn't the butler. If the murder happened with a rope, then it was in the library. And the third finding says, the Duke is not the murderer. And there are 4 other findings which are stated over here. You may look at them, you may read them in detail. What I have done here in the lower part, I have represented these verbal explanations in a formal way as OCL invariants. So, for example, the second finding, if the murder happened with a rope, then it was in the library. It is represented here in terms of the invariant finding 2. When the how, so this invariant is formulated in the context of a murder. The murder is an association class, and the association class has roles how, who, and where. And the second finding is now formally represented as a constraint. If how.name is equal to rope, this implies where.name is equal to library. And in very much the same way, all these 7 findings are represented as in a formal way as invariants over here. So we have 7 invariants which fit to this class diagram. We have here a partial object diagram. So in the verbal explanations, what is mentioned here, several tools are mentioned, the hammer, the rope, the knife, and the gun. And several potential murderers are mentioned. The butler, the Duke, and Adam is mentioned. So butler, Duke, and Adam are potential murderers. The contest is not mentioned as a option here in the verbal explanation, but this is what you as an inspector know from the context. Furthermore, there are in the verbal descriptions 2 places are mentioned. The library and the dining room, and you find them over here, the library and the dining room. And you know there are 2 other potential places, locations where the murderer could have committed his or her crime. That's the garden and the kitchen. So we have here a partial object diagram which fits to the class diagram, And what you now want to have, you want to have a link for this ternary association, and the link is missing here in the object diagram. The link should represent should identify the murderer, and well, that's another job that you can let the model validator do. And when you ask the model validator to consider these invariants and this partial object diagram, the model validator will tell you, well, the Countess is the murderer, and she has committed the murder with a hammer in the dining room. This is the only option when you carefully consider and analyze these constraints. Let them be formally represented as invariant, or let them be informally represented over here. Then you have only one choice. So the Countess is a murderer. And that was a second use case, the object diagram completion. The third use case, I have called it invariant independence. As an example, I have considered here an example which comes from the field of database systems. You may regard this here as a schema for a relational database. There are two relations, one relation town, one relation country. The relation town has two attributes. That's the name of the town, and there's a second attribute, CNAME. The attribute CNAME in town should refer to the name of the country in which this town lies. And the second relation is the relation country, which has only one attribute, name. We have two primary keys. The primary key in the relation town is the attribute name. The primary key in the relation country is the relation name, is the attribute name in the relation country, and we have a foreign key, CNAME. The attribute CNAME in the relation town is a foreign key which points to a country tuple, and it identifies the country in which this town lies. So we have a valid state over here. We have two towns. We have the town Elmwood and Oakwood, and we have the country Blueland, and Elmwood and Oakwood both lie in the country Blueland. And there's another country present here in this database state, or in this object diagram. That's country Redland. There is no town which lies in this country. There are only villages for this country. And you see here the all class invariants are satisfied in this database state. And what I'm going to do now, I'm going to systematically consider the three invariants which I have formulated over here, and I have negated each, and what I will do, I will negate each single invariant, and I will let the model validator construct a database state. I will let the model validator construct an object diagram which violates exactly one constraint. So I have negated here the primary key requirement for the country relation, and you see here you have two country, two tuples in the country relation, and both tuples have identical, they are different tuples, but both tuples have identical values for the name attributes. So this is a database state which satisfies a constraint. The primary key for town is satisfied. The foreign key for town is satisfied as well. But the primary key for country is violated here. So that's a database state, that's an object diagram where one constraint is violated but the other two constraints are satisfied. In much the same way, you can negate the second constraint and you will obtain an object diagram, a database state, where only the second constraint is violated, and in much the same way, you can negate the third constraint and you will get a constraint where only the third constraint is violated and the other two constraints are satisfied. So what we saw now, we saw three database states where exactly one constraint is violated, and taken together, these three database states, these three object diagrams prove invariant independence. They prove that it is not the case that the conjunction of two constraints implies the third constraints. The constraints are really independent from each other, and so the model validator can contribute to checking this formal property invariant independence by systematically constructing object diagrams where exactly one invariant is negated and the other constraints are satisfied. So I've been talking a little bit about the tool use. I've been talking about the model validator. The model validator is a component in use that is able to construct a UML object diagram starting from a UML class diagram. The UML class diagram may be augmented with OCL invariants. And for working with the model validator, you need to configure the model validator and you need to tune the model validator. You need to tell the model validator, you have to give the model validator a finite search space, a finite collection of object diagram among which the model validator has to find the proper solution. So the use cases I have been talking about were object diagram construction, partial object diagram completion, and checking a property like invariant independence. There are other use cases available in the model validator that are not covered in this presentation. Thanks for your attention.